Hello, today we will start orbital angular momentum in quantum mechanics. We have orbital angular momentum also in orbital mechanics, but the quantum mechanically we will deal it in a different way. And the formalism for the quantum mechanics, it is different from the orbital angular momentum. And we have already studied this orbital angular momentum in our high school physics, but it is a different one from this one, because here we will use in the quantum mechanics, and we will use three dimensional space here. So its formulas are different. The concept is the same, but the formulas are different. And we know that the basic definition of orbital angular momentum is L is equal to R cross P, where L represents the orbital angular momentum, R represents the position vector, and P represents the linear momentum of the particle. Here, as we are using the quantum mechanics, so we will use a particle, and mostly this particle will be the electron, which is moving around the nucleus of an atom. Let's suppose this is a system of particle where the central particle is basically a proton. If we are dealing with a hydrogen atom, because it's the simplest atom in all the elements which we know, because it is consisted only with the two particles. One is the proton and the other one is the electron is revolving around the nucleus or revolving around the proton. So the distance from the proton to the electron is usually represented by r. This is called the position vector, which we have written here. And at this time, any time, or at this particular time, the direction of the linear velocity of this electron will be tangent to the particle, tangent to the circle. And be remember that I am using here the word linear velocity, not the angular velocity. Linear velocity of a particle which is moving along a circle or an ellipse is different in every point along the circle, because the value and the direction of the linear velocity is the tangent to the circle. So if we represent that, here is the particle electron, so its direction will be the tangent to the circle at this point. And let's suppose if we say that the electron is here in another position, then the linear velocity will be tangent to the circle at this point. So the direction of the linear velocity will change point to point on the circle. So here we can say that this is, let's suppose this is the particle and this is the direction of the velocity. And be remember that the direction of the velocity, linear velocity, and the direction of the momentum is always same. So if the direction of velocity is in this direction, then the momentum, linear momentum, will also be in this direction. Let's start now. Angular momentum L is equal to R cross P. When we take our system into a Cartesian coordinate system, then we will write the components of position vector in this way, that x I hat plus y j hat plus z k hat. Here x I hat represent the x component of the position vector, and y j hat represent the y component, and z k hat represent the z component of the position vector. And we remember that we will not write here the arrow sign because on the x or on the y or on the z, because when we will write the vector, let's suppose this is a vector a, it will be equal to, according to the definition, magnitude of a multiplied the unit vector. So this will be the magnitude, not the vector. Both of these two, unit vector and the magnitude, when we multiply both of these two, then the result will be a vector. So this is the magnitude x, y and z. These are the magnitudes of along the x direction, y direction and z direction of the position vector r. Now this is the cross multiplication, and p is the momentum. As I told you before, its direction will depend on the direction of the linear velocity. And when we represent this momentum in a Cartesian coordinate system, then we will also write its three components: px I hat plus py j hat and plus pz k hat, where px, py and pz represents the momentum along the x direction, y direction and z direction. Okay, and B, remember that Px is the magnitude and I hat is the direction. So both of these two will represent the component. Not only Px is the component. Px I hat is the component of momentum, linear momentum along the x direction, and same Py and Pz. Now we have studied the cross multiplication and dot multiplication in our high school physics, that when we cross multiply or dot multiply with the two brackets, then we multiply the first component of the first bracket with the first component of the second bracket, and then the second and then the third component of the second bracket. This is the first bracket and this is the second bracket, and after that we will multiply the second component of the first bracket with the first component of the second bracket, and with the second component of the second bracket, and with the third component of the second bracket, and also the same with the third component. Okay, now we'll start the multiplication. Multiply first with the first, x multiply px. Here we can write cross or dot, it doesn't matter, because px and x, both of these two are the scalars because they are the magnitudes. The real thing is I hat and this one I hat, because these two are represents the unit vectors or the base vectors. So here we will be careful in writing the symbol of the multiplication. Is a cross, so we will write here cross, and if here is dot, then we will write here dot. Be remember this. This is more important when we are writing or when we are dealing with the vectors. Here we are dealing with the component, magnitude. Px and px are the magnitudes of the position vector and of the momentum. So I hat cross I hat cross I hat plus. Now we will multiply the first component of the first bracket to the second component of the second bracket, which will be equal to x multiplied by py, and now we are dealing with the unit vectors, so be careful. I hat cross j hat, and be remember the order. The first unit vector will be written in the first and the second will be written in the second place. We cannot change its order, because if we will change the order, then the all multiplication will result in a wrong direction. Okay, now first component of the first bracket will be multiplied with the third component of the second bracket, which will be x multiplied by pz into I hat, the first one vector, cross k hat, the last. Okay, plus, because this is not our complete one step, our step will be in the 3 lines. Now we will multiply the second component of the first bracket with the first component of the second bracket, and then second component of the second bracket, and then third component of the second bracket. Y px, y multiplied by px, and be remember the order. J is in the first place, cross, and I in the second place, plus. Now y with py, y with py, j hat cross j hat, plus y with z, y with z, and the unit vector will be j hat cross k hat. The third one, the last one, z multiplied by px, z px, unit vector will be k hat first cross I hat, plus again third component of the first bracket will be multiplied by second component of the second bracket, z py into k hat cross j hat, plus z with pz, z multiplied by pz into k hat cross k hat. Okay, now we know that the cross multiplication and also in the unit vectors, they are cyclic. They are cyclic or clockwise. If we write here I and j and k, this is a cyclic or clockwise rotation. If we multiply I with j, this is clockwise, I is j, then the result will be k and plus k, because the multiplication is in the clockwise direction. And if we multiply j with k, then the result will be plus I hat. Okay, and if we multiply k with I, it is also clockwise, then result will be j, third one vector j, but positive j. Okay, if we reverse the order, if we multiply I with k, it is opposite, it is not clockwise, anti-clockwise. I with k, the result will be next one j, but negative j, because now the multiplication is in the reverse direction, or in the reverse opposite direction, you can say. K with multiply j will be equal to the third one I, but in opposite direction, negative I. J with I, if we multiply j with I, the result will be k, but in opposite direction, negative k, and we will use it here. And be remember that whenever we will multiply the same vectors, unit vectors, with each other, then the result will be 0. It is a null vector. I cross I is 0, j cross j is 0, k cross k is 0, because 0 is multiplying with this one here, here, and here. So all of this component, or all of this term, will be 0. We will not write this one. Okay, so I cross I is 0, so this, all this term will become 0, plus xpy. Now represent, now check it, I cross j here, I cross j is equal to plus k. We will write here k hat. Okay, the next bracket, pxpz, xpz, sorry, I cross k. Now check here, I cross k, it is anti-clockwise. This is the clockwise order, and this is anti-clockwise order. I cross k, check here, I cross k. I cross k is equal to j, but because this is an anti-cyclic, so j will be negative, minus j hat. Now this one, plus ypx j cross I. J cross I, because it is acyclic, so k will be negative k hat. Okay, here ypy, but here is j cross j. Because of this j cross j, the result will be 0, so it is 0. This term, all this term is 0. Here ypz j cross k. J cross k is cyclic, so result will be I, and positive I, because it is cyclic. Now zpx k cross I. K cross I is cyclic, so plus j. For plus j, we don't need to write here plus sign. Okay, and k cross j, zpy k cross j, it is opposite, so I will be represented in negative I. Okay, so here we will write all of these terms in such a way that first of all we will write I, and then j, and then k. Let's start. This is I, and this is I. So ypz plus minus zpy, and the common in both of these two terms is I hat, and then j. This is the j, and this is the j. First of all, we will write here this one, zpx, because this is a positive and this is negative, plus minus xpz. What is the common between these two terms is j hat. And now k hat. This is k hat and this is k hat. We will write here xpy minus this plus minus and ypx. The common thing is k hat. This is the value of the angular momentum vector. This is its x component, this is y component, this is z component. Okay, here L is the angular momentum and orbital angular momentum, and this is the x component of the angular momentum, so we can say that Lx I hat, plus this one is the y component, so we can say that Ly j hat, and the next one, the last one, is the z component, so we can say Lz into k hat. Okay, this is our angular momentum in the vector formation, in the vector form. Now we will start to write the angular momentum operator. Angular momentum vector and operator is little bit different when we write them. This is the vector, angular momentum vector, and when we want to write down the operator, then we have to write here the cap. One cap only above the L vector will represent the operator of the angular momentum. Okay, this is equal to not r small r cross p, this is equal to r cross p. When we write down only the small r, it represents the position vector, and when we write down the capital R vector with a hat over it, it represents the operator of the position vector. And operator of position vector is equal to capital X hat I hat plus Y plus J hat, X, Y and Z. This is called the operator of the position vector. And operator of momentum P is equal to, we have been proved it before, and it is equal to minus iota h cut del, where del is a vector operator and its value is curly by curly x I hat plus curly by curly y j hat and plus curly by curly z k hat. Or we can say that if we multiply minus iota h cut with each of these three terms, we can get minus iota h cut curly by curly x I hat plus minus minus iota h cut curly by curly y j hat and minus curly by curly z with iota h cut, iota h cut curly by curly z k hat. Then it will become px I hat, and this is the operator, x component of the operator plus y component of the momentum operator plus z component of the momentum operator. Okay, now this will become P. We know that the momentum of operator of the momentum is equal to minus iota h cut del, or we can say that minus iota h cut, because this is the constant value, so we can write it before the product, and r cross del will left here. This is the cross product. Okay, now if we will write down the value of operator r and operator del, it will become this thing. Del operator is this one and r operator is this one, and if we cross multiply all of these three things, as we have been crossed the r and p before in the angular momentum, which I have written here, this is the value of momentum of orbital angular momentum, and if we multiply these two things again, we can get the same result but in a little bit different way. It will become Lx is equal to minus iota h cut y curly by curly z minus z hat curly by curly y. This result is the same as this one. Y, here we represent y small and here we write down the capital Y. Here it is written that small z and here is the capital Z. Only this is a different thing. The value of y, Ly will become minus iota h cut and z curly by curly x minus x hat curly by curly z, and for the last term Lz is equal to minus iota h cut x hat curly by curly y is the capital X, which represents the operator along the x direction, minus y hat curly by curly x, and here also we will write down the capital. All of these three letters x, y and z will be written in the capital letters. Hope so you can understand it, and if you have any problem in understanding this, you can contact me on my email, and also you can write down the comments in the video. Goodbye.